Welcome back to Vibrations Week 3. This is video 3. So in our previous video, we got the equation of motion for damped free vibration. And we had 3 different cases. So I want to talk about the underdamped case and the constants that we would find from this. All right, so here is the equation for underdamped, where we have E raised to the minus damping coefficient divided by 2 and the mass. All right, so that C is divided by both 2 and m. That's raised to the T. And then we have the C1 times the sine of our damped natural frequency times time plus C2 and times cosine of the damped natural frequency. There you go. All right, so I didn't do a great job with some of these subscripts here. Let me make that look like a subscript. This too looks like it could be a dt when it's supposed to be omega d times t. All right, so our initial displacement we could call x naught. All right, so that's small x. If we do that, first off we have e raised to the 0, right, because that's t is 0. So, and then we have c1 times the sine of 0, which is 0, plus c2 times the cosine of 0, which is 1. So therefore C2 is equal to the initial displacement. So that would be like if we took a spring or took a mass with a spring and a damper in it and we just pulled it down in initial displacement and let it go. This would be the answer. This would be the response, would be xo times this right here. And if we did not give it an initial velocity, that sign wouldn't be in there. So this would be the behavior right in there. So we have it right away. So the initial velocity, I'm just going to move this up just a little tiny bit. We're going to say that's going to be x dot. So we need to take the derivative of everything up here. So let's, oops, let me come back to that. Let's make it nice and purple. I want to give myself a lot of room here, so I'm going to go x dot is going to be equal to, well, first we have to take the derivative of this portion of it and multiply it by the remainder of the rest. So we have a negative c over 2m, and then it's times e to the negative c over 2m times t, and then everything we had here is c1 times the sine of omega dt plus, and then we'll go ahead and put the xo in there because we know that to be true, cosine of omega d t, right? But now we need to take the derivative of this, multiply this thing, and then times the derivatives of the other part right here. So it's going to be plus e to the minus c over 2m t, and I'm going to have to squeeze a little bit here. So it's going to be c1 omega d cosine of omega dt. Right, so that's kind of messy. I'll try that a little bit better. Omega dt, and then minus, is that true? Yeah, minus x naught omega d sine of omega dt. Okay, so now we want the initial velocity. So we have x dot of 0. Of course, that's x dot naught. And let's see what we can get rid of here. We'll start out with negative c over 2m. So e to the 0, so that's good, times c1 times 0, so that doesn't count for anything, plus x naught times 1, right? Because the cosine of 0 is going to be 1. So, all right, now continuing on, we go plus e to the 0, and then we're going to have c1 times omega d times 1 minus x naught omega d, but that's going to be times 0. So collecting all those things, let's see if we could find out what C1 is equal to, right? So that doesn't show up anywhere. So I'll just do another step right here. Negative, not 2, but C over 2m times x, all right, plus C1 omega d. All right, so the answer, if I did this correctly, should be C1 is equal to x naught, the initial velocity, plus c over 2m times the initial position divided by the damped natural frequency. So if we're going to write an equation for using these initial conditions, so the complete equation for this would be e to the minus c over 2m t times x naught dot plus c over 2m x naught divided by omega d times the sine of omega dt plus x naught. I didn't mean to make that the big one, right? So just the initial displacement times the cosine of omega d times t. So that is the big equation here for our underdamped displacement or position versus as a function of time. Things that we should remember about this is that this damped natural frequency can be found from k over m minus c over 2m squared. And another way of writing this, let's see, I don't quite like that, continue with that color, so let's switch on. We could also write this square root of the natural frequency squared, right? So this is the undamped natural frequency, minus c over 2m squared. Something that we don't do quite often on much of this, we have the damping factor, which I think I've already mentioned that I'm using the wrong Greek symbol, but it's something I got used to doing, so I can't unbreak my habit. We know that that's going to be the ratio of whatever our damping frequency, damping coefficient is divided by the critical damping coefficient, which is also equal to c over 2m omega n. So what we could do is part of the, and by the way, things to know about the damping factor is that if it's equal to 1, we are critically damped. If it is less than 1, we're underdamped, which is really the one we care about the most often because it has it still is a vibrating thing. Critically damped is not actually a periodic motion. And then if we are greater than 1, we are overdamped. And frankly speaking, critically damped is kind of difficult to achieve because you have to have the values work out exact, right? So that the m times the natural frequency has to equal the damping coefficient that you have. It has to be exactly correct. So getting that to match up perfectly is, maybe there's some amount of margin that it can be within, but we're generally going to be either overdamped or underdamped. I marked those the other way, either underdamped or overdamped. We can sometimes we will write this right here. I think I'm going to mess this up. Maybe not. We can massage this about here and go 1 minus this right here, the damping factor. So that's a pretty good looking equation right there for things, right? Kind of gives sort of an impression overall on how to get the relationship, I should say, between the damped natural frequency and the undamped natural frequency. You'll notice that the damped natural frequency is always going to be less than the undamped natural frequency, right? So because we're going to subtract from 1, and this is always going to be squared, so it's always going to be a positive number, so it's always going to be the square root of something less than 1 multiplied by the natural frequency. So that's kind of useful. Let me check and see what we're doing here. I'm going to end the show, discard this stuff, and I want to see our time. We're at 11 minutes. I did want to bring up this Excel spreadsheet that I've made. And if I happen to post this on the internet, please don't ask me for my spreadsheets. I'm not giving stuff away to people. This is an interesting setup here, and let me see if this will allow me to yeah, I think that's going to work. Okay. So I just moved my Surface notebook here. I swapped it back up to vertical. You can check out from this, and I have a couple try these types of things. So this first one, you can see this. You can see that it's damp. The red is the damp is the graph, and the black is without damping. But I could try, and I could reduce the mass of this. You can see what the frequencies go. So let's see. We could also increase it if we wanted to. There's maybe increase it to 4. You can see some of the facts. It doesn't look all that much different. But okay. So here we could change the damping to 2. So I reduce the mass and I increase the damping, the coefficient to 2. And you could see that what we have, where are we? Where's our damping? Okay, so we have we still have a 0.707, but we got really close to getting to this overdamped, right? So we can see that right. Let's see if we try here. We go 2, 1, 2, 1, right there. That's close. Let's go for 2, 2, 3. And 3, boom, and that's a 0.75. So still not a critical damping. All right, here. So let me see if I go 3.9. All right, so 2, 2, and 3.9, boom. And I need to change the scale right here. Let's see if we change the scale or format my axis. And I probably only want it to go, let me go to the major units and go stop at 10. Right there. Oops, not great. But you can see it's not a vibratory action. And if we come back up to here, you can see that we're still technically underdamped at 0.975. But if I go to 4, boom, you get it all divided by zeros. So I'm going to undo all these things. Let's see, I'll go back to the default one right here. 2 and 1. So you can play around with this and probably find the solution to some problems by messing around with this. But if you go ahead and take a look, let's see, this guy right there, that is going to be this equation right in here. That charts out, right? And if you take a look at the information back up in here, I don't think I have initial conditions in. It might have the initial conditions are probably going to be some type. I'm trying to look for there. Maybe I should leave that up to you. Right? Well, actually, you can see here's the equation right up in there. You can see what my equation is that we're messing against, and it has an XO right as part of it. So what is my XO? Oh, I guess I'm just basing on 1 right there, right? So I don't have any initial conditions assigned with this, just a 1 as being the value. You could also, we're going to talk about this log decrement thing soon, coming up, where you can kind of see these two different auxiliary lines that help you to see where the fade is. Is it's decreasing like a log decrement. I think maybe that's what I mean by decrement. But anyway, we'll talk about that.